Yeah, thanks a lot, Adesh, and thanks a lot to you and to the team for organizing this event. I think this is really great, and yeah, thanks a lot for the invite. Is my video working? Also, can you see him?
Yes, yes, yes. Your video is working. You can actually present it, I think.
Share my screen. Perfect. So you should see. Wait a second. Now you should see it. Just a second. Okay, so I think now I have the setup that I need here. Okay, yeah, thanks a lot.
Perfect.
Actually, I had thought that this will start 1 hour later, but I think I made it almost in time at least. And yeah, I mean, you already briefly introduced me. I'm Jan. I'm an IBM Distinguished Engineer, and also started mathematics, applied mathematics, actually a combination of mathematics, mechanical engineering, and computer science. At that time, that was called in German Techno-Mathematik. I studied in Clausthal-Zellerfeld, which is more in the north of Germany, and did my PhD in 99 in Karlsruhe at the KIT, which was not called KIT at that time, but which is now the KIT. And actually, a week after my PhD, I joined IBM, and ever since then, I'm working with IBM. My role is a technical pre-sales, so I'm a technical expert in a pre-sales environment. So I'm working with various clients over that time, advising them and trying to understand what their challenges are and how we can help from the IBM side with different kinds of innovative products. Actually, when I started with IBM 25 years ago, Linux was new and innovative. So that was the first topic that I was involved in. Various other things over time. And since 2017, I'm very interested in quantum computing. So since then, I became a Qiskit advocate and an IBM Quantum Ambassador, which is a role that only exists in IBM. But Qiskit advocates, probably as you know, and I will share one chart on that a bit later. Qiskit advocates is something that probably some of you already are, and that others can become, yeah, if you like and if you enjoy working with Qiskit. Currently I have two roles in IBM, and the one that is related to quantum computing is I'm the IBM Quantum Tech Sales Lead for the DACH region. In that capacity, for example, I lead the IBM Quantum Ambassadors, and I join quite a number of events virtually and also in person and focused on the DACH region. Right. So let's start with the presentation. So it's not I would call it not a typical IBM presentation. It is more about with the fun and entertaining side of quantum computing, which I also enjoy beside of the day job and the real job that I have. You are welcome to ask questions. Let me see if I can see the chat. And so I assume that you can unmute, and from time to time I will also have a look at the chat if there are any questions or comments on it. Okay, so as you can see, this is a presentation that I gave earlier this year at a large conference that we were hosting. It was called IBM Tech Exchange. There are a few conferences with that name. There's a worldwide one, and then also regional conferences, and this was the Tech Exchange in EMEA, which happened in Barcelona earlier this year in January, obviously. Right, so let's have a look at the agenda. I would, as I mentioned, it's a bit about the fun and entertaining side, but also educational. Yeah, so the things that I would like to introduce are also where people can learn not really the research frontier, but more an introduction and the fundamentals of quantum computing. Okay, so yeah, this is the agenda, and we will have a look at most of these topics and projects. Most of that are open source projects. Yeah, so you can find them on GitHub, and I would be very happy if you're interested in them and use them or even contribute to them. Yeah, and please, if you have any questions on that, also after the presentation today, please reach out to me. I think it would be easiest to find me on LinkedIn. Yeah, I mean, you have my name, and then just contact me on LinkedIn, and then we can take it further from there. Good. So there are a few projects. First is an introduction to, or a first introduction to some of the principles of quantum mechanics and quantum computing. So we will have a look at a coin game, yeah, that uses a single qubit and kind of introduces a superposition. Yeah. And afterwards, we have a few other games or serious games for quantum computing. And the high-level concept is always the same. Yeah, there are certain very specific rules. Yeah, if you know a bit more about quantum mechanics and quantum computing, then you will immediately understand why the rules are made in this way as they are. And typically, so there's a game or a task that you should solve, or that the player should solve. And if you play that with classical rules and with classical kind of moves in the game, then you cannot win the game. Yeah, or it's just by pure chance, by pure random who wins. And if one of the players then uses some quantumness, so some quantum moves like superposition or entanglement, then this player can win the game, yeah, with probability 1. And that lets people wonder, I mean, how is that possible? And what is that special quantum property that is being used and that is being exploited there? And then typically these games, because they are serious games, so it's not about the like front end and high-end graphics, it's more about the educational content that is delivered with it. Then the games also explain, yeah, what how that works and what is behind that. Okay, so a few games, we will have a look at them. Then we will have a look at a very special project that is about building a functional model of a quantum computer at home. So the Raspberry, I also have one model with me. I can show it in a couple of minutes. That is a project where we combine 3D printing, so a 3D printed model of our quantum system 1, quite small model, Raspberry Pi and Qiskit. And Qiskit obviously can be installed, or maybe not obviously, but Qiskit can be installed on a Raspberry Pi. And then you can, Qiskit includes the Qiskit Air simulator, and then you can execute simple quantum circuits on the Raspberry Pi that is inside a model that looks like the quantum system 1. And I think that's quite nice. Then there's a coffee maker. I will just explain that later. Yeah, that is based on top of that Raspberry project. Then some more things on project that you can find on the internet, like the quantum paradoxes from Maria Violaris. We will have a look at that. And then for different projects for different ages of children, who and to kind of discuss about quantum computing with them. And maybe also for some of you, that is nice because, I mean, if you do something related to quantum computing, it's not always easy to explain that to friends and family, what you are doing, what we are doing. And these are some nice things that have a serious background, but also are also good to explain. Okay, then we have two other projects. One is a car configurator. I will explain that later. And a racetrack, so actually a physical racetrack that where the cars are controlled with quantum machine learning in an attempt to go as fast as possible around that racetrack. Okay, and then if we have time at the end, I can mention some more serious aspects of quantum computing and Qiskit up to becoming a Qiskit advocate, for those that are not aware yet. Okay, let's get started. First, the coin game. And actually, it was introduced quite some time ago. And let's have a look at this one. There's also a YouTube video made by Shohini, and it's explained in 10 minutes here how this coin game works. It uses a single qubit, and then there are two players, and then there are some specific rules. The coin is hidden, and the players turn around that coin a couple of times. And then depending on if at the end it shows heads or tails, then then one of the two players wins basically. And it is so I don't want to explain the rules in detail, but it's quite simple. So you can probably guess that if the coin is hidden and both players one after the other turn around the coin, I mean they do not see it. Okay. So I should mention that. They are allowed to turn around the coin, but they can also leave it as it is. Yeah. And so the next player does not know what the previous player has done, so they do not know the state of the coin, if it's heads or tails. And so it's pure randomness here, pure chance who wins at the end. But then you can change the rules, and you can kind of allow one of the players to put the coin in a superposition state. Yeah. Basically that does not change if the other player then turns the coin around with an X gate. Yeah, I mean that's at the end of the quantum computing implementation of that. And then that one player who is using the quantum move can win this game with probability 1. And we also have implemented that game. I will show that a bit later. Yeah, so that people can kind of play that online, and that online version then also includes an explanation, really also the formulas. Yeah, what is a quantum state? How is that defined? How do you apply a gate? Yeah, for a single qubit, not for multiple qubits. And obviously the Hadamard gate, yeah, is the one that is applied to create that superposition. And then also the formulas of the calculation is shown, and why this works at the end, and why that one player can win. Okay, we have also written a publication here where this is discussed extensively, including the formulas, but also in the online version it is described very concise. Okay. So the next example is a visualization of the Bloch sphere. And I can share, of course, the charts and the handouts afterwards with you, so that you can use all of the URLs if you like. This is a web page that was created by a colleague of mine with an interactive visualization of the Bloch sphere. Yeah. And many of you will know that the Bloch sphere is a representation of a single qubit that shows the state, or can illustrate the state of the qubit, and how to apply single qubit gates. Yeah, it does not work for multiple qubits. And in this online version, so this is just a screenshot, but in the online version, then you can apply various gates to that Bloch sphere. And you can also turn it around and then kind of see and analyze what the status is, and understand how these gates act on that qubit. So that I think is a very nice illustration here of the Bloch sphere and for a single qubit. Then this chart is some things have changed, but the quantum composer, the circuit composer, that is still available on our website, and that is a graphical tool that people can use to create simple quantum circuits, and that is kind of the next step after looking at the coin game and the visualization of the Bloch sphere. And here you can, with drag and drop, you can create circuits with a few qubits. So not only 2, you can have more qubits, but not a large number. And obviously it is limited, the size and complexity of circuits that you can create with drag and drop. And if you log in on that website with an ID that is free of charge, you can then execute these circuits on real quantum computers from IBM free of charge. And that is really nice, and I think that's a fantastic possibilities that we have in really trying this very new and future technology out. Okay, then I should make a comment about the Quantum Lab. Yeah, that was an online environment, a Jupyter Notebook environment that does not exist anymore on the IBM website, but there are alternatives that you can use. Yeah, so basically there are various alternatives for online Jupyter Notebook or Jupyter Lab environments. And some of them already have Qiskit pre-installed so that you can use them to use or with the first steps in using Qiskit, yeah, our quantum SDK, which is then the next step after using the drag and drop here. Good. Next section is about the serious games for quantum computing, and especially one project that you can also find on GitHub. It's called Fun with Quantum, or funwithquantum.org is the URL. And it includes several games. Yeah, so one game, which is kind of the next step after the coin game. As I described, the coin game only uses a single qubit and explains a superposition. And this GHZ game that uses 3 qubits, it's then based on the GHZ state. Yeah, and again, there are rules and there's a plot for that game that the players want to escape from an evil wizard. And again, if you apply just classical rules and classical moves, then they cannot win this game. But if they use quantum computing, in this case the GHZ state, which is an entangled state of 3 qubits, then they can win this game with probability 1. Okay, and the coin game and also the GHZ game and some other introductory examples, they are available and they are implemented in a GitHub repository, which is called funwithquantum.org. So it has the coin game, and that is connected with MyBinder. So if you go to that GitHub page and then you call and then there's a button included there, which you will see, which then launches this game or the Qiskit Python notebook with the implementation of that game in MyBinder, yeah, which is a free online service that also hosts Jupyter notebooks. Actually, for those who try it out right now, there was an issue with some of the requirements and dependencies. So actually, I'm afraid as of today it does not work, but we are in the process of updating this repository and the Qiskit code to Qiskit 1, and then hopefully in let me say in 2 weeks it will work again. Yeah, so don't worry if the MyBinder integration does not work today, but very soon we will have that fixed. Okay, some other things. As I mentioned, the GHZ game that is also implemented in this repo. And then a very interesting aspect, of course, is executing that on real hardware. And as I have explained, that game, yeah, at least in theory, you can win that with probability 1, yeah, by using a GHZ state and exploiting entanglement. But as probably all of you know, real quantum computers as of today are noisy. And so the results are not perfect. And then we tried this game on a real quantum computer. And actually, in the first attempts, the winning probability was something like 70% or so. Yeah, so that was not good. And I would not bet on that in a real case, yeah, when trapped by a wizard. And then in that notebook that is in this repository, we discuss multiple approaches how to deal with these error and noise effects. So a simple one is like you just choose the best qubits in a device because we only need 3 qubits, and all of today's devices that we have more than 100 qubits. So you kind of can use the best or some connected very good qubits. And there are other approaches, including measurement error mitigation, which is also applied. And I find it quite impressive that with these simple techniques, so we are not using things like predictive error cancellation or zero noise extrapolation, which would be much more advanced. But with this simpler and more easy to understand error mitigation techniques, we could get this the winning probability from around 70% to 95%, which I found really impressive. So, and then there's one other example in that repository that's about solving Boolean satisfiability problems with quantum computing and with Qiskit. And actually, the code that you can see here, that is basically the whole code that is needed. And because Qiskit can import such a Boolean expression and then generate an oracle and apply the Grover's algorithm to solve that problem. And this example is not so much to explain how that really works on a quantum computer, so we do not discuss Grover's algorithm in detail, but it's more to show how easy it is or how easy it can be, how easy it will be to use quantum algorithms. And I mean, obviously you need to define the problem, but then it's just a few lines of code to actually call a quantum algorithm that solves this problem and then outputs the result. Okay. So yes, you're very welcome to have a look at this repository. As I mentioned, the Mindbinder integration does not work as of today, but we are updating that to Qiskit 1. Good, now a quick chapter on some more serious games for quantum computing. And if you search the internet, there's quite a number of games that you can find. Some of them are web-based. Some of them, there's an app for smartphones, for mobile phones. So this one is Hello Quantum. That was created also by a former IBMer. We have Qiskit blocks, tic-tac-toe with quantum rules, and some more. There's also a quantum chess version. And I had a student, a bachelor student, Isabel, and she wrote her bachelor thesis about these serious games for quantum computing. And actually, then she implemented this GHC game, which I have mentioned before. Good. Now let's have a look at the Raspberry project, which I think is really special. And I already mentioned, so we call it a functional model of our IBM Quantum System 1. And I mean, what means a functional model? As I mentioned, it is based on 3D printing. So a 3D printed housing or model of the IBM Quantum System 1. It includes a Raspberry Pi and Qiskit, which can be installed on the Raspberry. And now, obviously, that does not make it a quantum computer. So it's not a real quantum computer, but with the AIR simulator that is included in Qiskit, you can execute simple quantum circuits on that device. On the right-hand side, the picture in the middle, that is actually the real system, the real IBM Quantum System 1. And above and below, these are pictures of the model, of the Raspberry model. And let me forget the one here. Yes. So there are two sizes of that. This is a bit larger one. Okay, so, and yes, I think you can recognize that it looks like the IBM Quantum System 1. As you can see, we have LEDs integrated here, which can be used to kind of display the state of a number of qubits. And the Raspberry Pi is included here in the bottom, so we have all or most of the interfaces of the connectors accessible, like USB, network connector, HDMI, power, that is accessible here. So you can also connect an external display, for example, to it. Yeah. The battery pack is included, so that really runs cable-free if you wish. And we have started with that project in 2020, and it was shortly before the first quantum computer, the first IBM quantum computer, was installed in Germany, in Ening, a bit south of Stuttgart. And the opening ceremony that was mid of 21. Angela Merkel, who was our chancellor at that time, she joined that ceremony virtually because it was a pandemic time. And we sent one of these models to her, to the chancellor's office, which of course was very nice, for us as an open source project, really to end up in the chancellor's office. Okay, and there are a number of demos that run that are pre-installed, basically on this Raspberry project. Raspberry.org, that is the GitHub site for that. And currently, you are aware that IBM has introduced a Quantum System 2 some time ago, and currently we are making a major update, and we have created and will release it probably end of November, a 3D printed model of IBM Quantum System 2, which looks very different from this one. And there are also major upgrades to the software stack. For example, we are moving to a 64-bit environment, so the old project here is 32-bit. We are upgrading to Qiskit 1, to Qiskit 1.2, including additional demos like the quantum paradoxes, which I will mention in a couple of minutes. And a closer integration also into the Raspberry Pi environment. So you will be able to install additional demos and to use these demos within the Raspi config, so within the standard configuration tool that is being used on a Raspberry Pi. Maybe for those who have not heard or have not yet seen a Raspberry Pi, this is such a Raspberry Pi mini computer. Depending on the configuration, it costs between, I think, 50 and 90 euros. And the current versions, they have a quad-core CPU, so they are quite powerful. Good. So next section. This is a demo that is built on top of the Raspberry. And what we have done is we have replaced the user interface of a coffee machine, of a coffee maker, with a quantum computer. And actually, I don't have a screenshot here, but I can describe it. Maybe let's have a look at this website. Better. So this also is an open source project, except for the hardware, obviously. Right. So this is the real coffee machine, and this is the new quantum user interface. And as you can see, we are using the circuit composer that I have mentioned earlier. And so the kind of users can create, and this is a large touch display, can create with drag and drop a quantum circuit with 3 qubits. And with 3 qubits, you have 8 basis states, and each of the basis states is mapped to one beverage, so to coffee, espresso, cappuccino, and so on. And then the challenge or the task is to create a circuit, and at the end, we do a single shot and a single measurement. Right? And now the task is to create the circuit in such a way that the measurement result at the end corresponds to a beverage that you actually would like to drink. And so we have used that at a large number of events and always got a great feedback. So people thought this was a great idea to make quantum computing or the basics of quantum computing tangible. And in addition to using a perfect simulator, we can also use a mock device. which includes a noise model of one of our real quantum computers. So you can also see the effects of error and noise here, which then lead to get a beverage that you maybe did not want, and that would not have been an outcome of a perfect execution of the circuit that you have created. And that then leads to the discussion about, what can you really use quantum computers for? How do you handle error and noise and so on? So I think it's quite a nice demo. For those who are interested in the details, the demo runs on the Raspberry, but of course you can also run it on a laptop. And we are using an IoT API that is called Home Connect. That's from BSH or Bosch Siemens Hausgeräte. And with that, you can not only connect to a coffee maker, but also to your dishwasher and any other equipment. But we do not find a good use case for that. But with the coffee maker, that works really nice. Yeah. And so in this demo, at the end, after you do this one shot and the measurement, then there's a button where you can kind of accept the result. Yeah. And if you push that button, then the coffee maker gets triggered and produces that beverage. Okay, maybe I make a short comment of how we came up with that demo. And actually, it was maybe a year before we created that demo. I was presenting in a similar way as today in a meetup about quantum computing. And then someone mentioned quantum coffee maker and or quantum coffee machine. But not with a concrete idea of what that would be and how you would do that. And I was like, what a crazy idea. So that makes no sense at all. And then a year later, I was tasked in IBM with coming up with a demo for an event that includes some hands-on, but is easy enough to understand for everybody, basically. And then I thought, quantum coffee machine, that is a great idea. Yeah. And then we thought about the details and did the implementation here. And again, this is an open source project that you can access here on GitHub. Of course, it also works if you do not have this specific coffee machine with the Home Connect API. You can use the demo, of course, in the same way. And then at the end, if it says, okay, the result is a cappuccino, okay, then you have to operate your coffee machine manually and select manually the cappuccino and use this IoT API. Yeah, but that is also nice, I think. Good. Next thing is the quantum paradoxes that they were written, or it's a series by Maria Violares. And she has a YouTube channel and also a homepage if you Google that, and a blog where she describes, a bit similar to these coin game and the GHZ game, different, strange aspects of quantum mechanics and quantum computing, explains that and also provides an implementation with Qiskit, so that people then can have a look at and execute to get a better understanding of these very specific and strange effects. And that is actually something that we will also include in the new version of the Raspberry. In the Raspberry 2 project, we will also have these quantum paradoxes so that you can execute them locally in Qiskit 1.2 probably. Good, next chapter. That is about these projects for kids in different ages. And so for the smallest kids, for babies, there are really nice books or there's a series from Chris Ferry. He has books not only related to quantum mechanics or quantum computing, but also a lot of other science topics. And as you can see, they are really explained on for babies. And if you want to tell them or read a book as a good night story, that is really nice. So it is very simple, but I would say it is reasonably correct, yeah, explained. For example, what entanglement is or quantum computing. So that's definitely a nice gift, yeah, for someone who is working in that area if they have a child or a baby. Good. Then, sorry, next one, right, is a Lego model. And actually, that was kind of invented by my youngest daughter when she was 7. And so she built, I mean, she has seen many pictures of the quantum computer and also that 3D printed model. And so she was building a model of a quantum computer with Lego bricks. And that is also published like the bill of material and the build instructions on Quantigo, like quantum at lego.org. Yes. And I found it very interesting. I mean, it's not only about assembling the Lego brick, but then the children, depending on their age, also ask questions about it. Yeah, I mean, what is a quantum computer? Why is it, or what is different than normal computers? Why does it look as it does? Yeah, I mean, obviously, it looks very different from a normal computer. And then you can discuss about the cryostat and some interesting aspects there. And she was also asking, yeah, if we will have a quantum computer at home one day, yeah, and if it will be like the standard way of computing. And so depending on the age, you can have really relevant discussions about quantum computing, yeah, with kids of various ages. And in the meantime, there's also Lego model of the quantum system too, as you can. Good. Then, if the kids get a bit older, and so at some point, the parents need to have the talk, yeah, with their children, not about the birds and the bees, but the talk. And this is a cartoon which is much longer. So this is only the like I don't know, maybe 5% of or even less than of that whole cartoon. And I find it hilarious. Yeah. So the child is studying or looking at a book with quantum computing, and he does not want to discuss that with his mother. But then they speak about it, and so every time I read this cartoon, I understand that better because there's so much subtle humor included, always relating to some real quantum mechanics aspects. And so that is really nice. And the moral at the end is, so this is the end of that cartoon. It's if you don't talk to your kids about quantum computing, someone else will. Yeah, so better do it yourself. Good. Right, a couple of 2 or 3 other projects that I would like to mention. So the car configurator. I mean, we've often been asked about, or obviously, generative AI. Yeah, that is a hot topic that basically everybody is looking at. And now there's also the question of how Gen AI and quantum computing can play together. And there are different combinations. Yeah, I mean, obviously there's quantum machine learning. Yeah, and so you can run some machine learning algorithms, specific machine learning algorithms, or part of algorithms on a quantum computer. And I mean that will the value of that will increase with further progress on the hardware and software side with quantum computing, obviously. So that's one thing. The one other approach is that, of course, AI is being used today to improve certain parts or certain elements of the quantum computing stack. Of course, there's a code assistant, a Qiskit code assistant, yeah, as for other programming languages. And in the transpiler, yeah, there are AI-assisted or reinforcement learning, actually in that case, reinforcement learning-based transpiler passes that produce kind of better, more efficient quantum code or machine code. Okay, these are two ways to combine it. And then there's another approach, which I would like to discuss. And that is, if you see it, I mean, quite simple. At the end, I mean, people have a business problem that they want to solve. Yeah, and for solving that business problem, you can use both quantum computing and machine learning AI for different parts of that solution, yeah, of the whole solution implementation. And we have created, that was a year ago, I think, yeah, a bit more than a year ago, an implementation that, and this is the high-level concept. So there's the business problem. We are using WatsonX.ai, which is the IBM AI platform. The AI component kind of understands the business problem, then creates a mathematically correct formulation of that business problem, and that can then be solved on a quantum computer or also with a classical solver. Yeah. And to make it a bit more concrete, what we were doing or what we have actually implemented is a problem from the automotive industry, and that is a car configurator. And so I mean, it's different in different countries. Typically in Germany, people want to configure their very own and individual car. So they want to select or deselect any of the configuration options. Yeah. Of course, it is not possible to have any combination here. There are some exclusions or some dependencies. So at the end, for the manufacturer, that is a Boolean satisfiability problem. And there are two aspects to it. I mean, on the one side, there's a manufacturer, yeah, who knows about the restrictions in which cars can be manufactured. Yeah, so they know about these inclusions and exclusions, which of the configuration options have to go together or are mutually exclusive. And then there's the client, yeah, who has certain preferences and wants to select. I mean, what options do they want to have? Okay, so and now here the large language model, yeah, kind of understands a natural language formulation, yeah, of both sides from the car manufacturer, these inclusions and exclusions, and the preferences of the client, of the customer, and then creates a mathematical formulation. In that case, a Boolean expression, so a Boolean satisfiability problem. Yeah. And as I have mentioned earlier in this, when we discussed the Founders Quantum Repository, a Boolean satisfiability problem can easily be solved with Qiskit and with quantum computing. So you can import that and then solve it with Grover's algorithm on a quantum computer or on a simulator, and then return the result. Yeah, I thought that is a nice illustration of how to combine AI and quantum computing to solve a real problem. Clearly, as of today, we have not reached quantum advantage yet, so this is not yet better than a purely classical approach. And so I don't want to claim that we have created a better car configurator here, but I think a good inspiration, yeah, to think about how to combine AI and quantum computing. Good. So maybe the last example that I would like to show, that is the racetrack. I briefly mentioned that at the beginning. So we have or also a student of mine, he has implemented a quantum machine learning algorithm, which is using reinforcement learning, quantum reinforcement learning, to control a car, a slot car on this racetrack. Yeah, and the goal obviously is to go as fast as possible. And the car kind of, or the algorithm kind of learns where to accelerate, where to slow down, and how to go around this track as quickly as possible. Probably many of you would know this kind of track as a carrera, a racetrack. Actually, this is a different one. It's called Anki Overdrive. And the cars and the track, they have lots of sensors and an API that you can connect to get the state of the car. So on which track is it, what is the speed, and so on. So you can control it via a Bluetooth interface. So that was very well suited and for this kind of implementation and for this API access. And the result that we achieved was that basically the quantum machine learning algorithm is as good as a human driver. Yeah. So we so not as good as a pro driver, but as good as a normal human, yeah, who is trying that racetrack. Okay, and I mean, at the end, it was not about creating the fastest. I mean, it's about learning and illustrating quantum machine learning, yeah, and also learning things in that implementation. Right. Okay, so these were, I think, the projects that I wanted to introduce or give an overview. Let me just mention Qiskit advocates. So I assume some of you are already Qiskit advocates, and for the others, that might be a nice information. So there is a, sorry, I should go back one page. There's a Qiskit developer certification, yeah, which is a badge that where you can prove your hands-on skills with Qiskit. Currently, that is updated to Qiskit version 1. Yeah. And then the next step is you can become a member of the Qiskit advocate team, which is supported by IBM, by the IBM Qiskit team. There's a mentoring program, for example, and certain community events. And yeah, it's a nice community of people who are enthusiastic around quantum computing and Qiskit. And typically once a year, new advocates are being added to the team. Actually, currently, there's a bit of a transformation of that program, and it will be relaunched next year. And so this is a URL, or if you scan the QR code, you can add yourself to basically to a mailing list where you get information about the relaunch and about the new program when it becomes available early next year. Yeah. Okay, and of course I can also share that URL afterwards. Good. Okay, so I think that that's it. What I wanted to discuss. I hope there were some inspirations for you, yeah, for some fun and entertaining projects around quantum computing. So I will be available if there are any questions. Please unmute yourself or ask questions in the chat window. Okay. One question that I see is it possible to get discounts for developer badges for this developer certification? Typically, I cannot commit that for next year. But in previous years, typically there was a discount for those who applied to become a Qiskit advocate. Yeah. So my recommendation would be to watch out for the relaunch of the Qiskit advocate, or for the changes of the Qiskit advocate program, and for the next window when new advocates are being added. And I would assume, I would hope that then there's some support for those who want to become a Qiskit advocate, and also for that developer certification. Okay, other questions?
I have a question. Have you used any of the Quantum for Babies book in your personal life, maybe?
The quantum,
the little booklets that you showed, the Quantum Computing for Babies. Have you used any
yeah.
of them? Have you used any of them
So
yourself?
yeah, so I have used them also with my youngest daughter. And for me, an additional challenge was the books are in English. Yeah, so I always had to translate that to German for her. And yeah, so I mean, now she is 11. Yeah, she's not a quantum computing expert, but so she also found it nice and yeah, so I mean, it is something that is related to the work that I am doing, and so for her it was nice to have some relation and to the work that I am doing. Yes, I also have a book that I can show it now. Yeah, so that is the book, and really thick pages. It's really like for as typical books for babies. Yeah.
Okay, perfect. Thank you.
Actually, I'm not sure how many of these books actually end up in children's rooms, and how many are given for like a master's exam to physicists, yeah, or older people. Okay, other questions or comments?
Perfect. Yes. Hi everyone. Yes. So if you have any further questions, you can either unmute or you can write it in the chat. There's also a Q&A section if you want to type it there. But yeah, let let us know in a minute or two. And in the meanwhile, thank you very much for the talk. It was very inspiring and interesting with the games and a lot of games. With the,
Yeah, thanks a lot. And as I mentioned, not the typical IBM presentation. Yes.
yeah. Yes, Ahmed, you had a question?
Yes, I have a small
Yeah.
question. I'm really interested in the race car application you have previously shown us.
Yes.
I would like to ask a question. It might be a little bit naive, but why would I need to apply quantum computer instead of classical control or classical computing paradigms? I mean, when a classical computer is already working well,
Yes.
what difference would it bring?
Yeah. Right. So it's an excellent question. Yeah. And I mean, that does not only apply to this racetrack, yeah, but to many other like examples and things that are being done today with quantum computers. And as I briefly mentioned, quantum advantage has not been achieved yet, yeah, by nobody in the industry. So as of today, yeah, November 24, all practically relevant problems can be solved kind of better with a classical computer than with a quantum computer. Yeah. And the best research results that we have is this what we call a quantum utility, so being on par, on the same level with the quantum computing as the best classical approaches, yeah, but not really better. And now but the perspective or the promise of quantum computing is that hopefully quite soon, yeah, we will achieve quantum advantage, yeah, for the first specific applications, yeah. And when I say quite soon, we strongly believe that quantum advantage can be achieved before we have fault tolerant, before we have a quantum error correction, yeah. So within the next few years, yeah. And basically everything that we do now is to prepare for that, and together, yeah, with industry partners that we have, doing the research and identifying the applications, the real world problems, the algorithms, and where to achieve quantum advantage. Yeah. And in that sense, that's also with the racetrack. Yeah. It is, I mean, the racetrack, that is not about utility scale. Yeah. That is more about education and an illustration. But yes, I mean, I don't know if we further progress with quantum computing, yeah, and achieve quantum advantage, yeah, if you then would use a quantum computer for that racetrack, probably not. Yeah.
May I ask another question, please? You said that the car has the algorithm has proven to be working perfectly in like imitating a normal driver, how a normal driver reacts and so on. But this is pretty interesting because sometimes in autonomous driving algorithms, we have the problem that the algorithm cannot differentiate between a flying, for example, a plastic bag and a real dangerous thing.
Yeah.
So could such these problems and maybe in using quantum machine learning, could these problems be better handled or
Yeah.
handled in a better way?
Yes, I mean that is the hope or the expectation of quantum machine learning. Yeah, that better machine learning models can be created with less training data. Yeah, but
Hmm.
for this implementation, I mean we are far away from that. So we are not using image processing. Yeah, we are using really sensor data like the position on the track, the speed, and things. So more simple sensors, yeah, not graphics.
This is really important because sometimes data generation process sometimes is not ethical or sometimes maybe not possible. So working with less data is very, very vorteilhaft as
Yeah,
advantages for
yes.
yeah quantum computing or quantum machine learning algorithms.
Yeah. Right. And I mean that is for the different application areas of quantum computing, that it is different what specific benefits we expect currently. Yeah, so for machine learning, it is better models with less training data. For other areas, it is computing larger or solving larger problems faster. Yeah.
Mhm. Thank you.
So I have a question in the chat. Is quantum computing an engineering problem yet? What are the current challenges that prevents us from reaching quantum advantage? I think it was slightly answered, but if you want to add anything.
Yes. Also, excellent question. Um, there was so probably some of you are aware of the IBM quantum computing innovation and development roadmap. Yeah. So that is a roadmap where our research team says and gives an outlook what they want to achieve and what they want to make available over the next years. Yeah. And that roadmap is more detailed until 2029, and also is an outlook until 2033, which is quite far-reaching for a research roadmap. Yeah. And okay, so the question is it an engineering problem or a research problem now? And definitely in quantum computing overall, there is still a lot of research to do. Now, Jay Gambetta, in a recent presentation, he said that the hardware roadmap that we have, if you only look at the hardware, that is now an engineering problem, a hard engineering problem, but not research anymore, from his perspective. So his message is that basically we have identified all of the challenges, and we know well enough how to solve them. Yeah, how to scale the systems, how to get to the error rates that need to be achieved. Yeah, there are still many steps needed. Yeah, so that engineering has not yet been completed. Yeah, that will take a couple of years. But his clear message was for the hardware roadmap, we do not see any roadblock, and it is now a hard engineering problem and not a research problem anymore. Yeah. But again, so that statement was specifically for the hardware roadmap and not for quantum computing overall. Yeah, in terms of algorithms, also quantum error correction, yeah, a lot of research still needs to be done and can be done.